This is the third part of videos describing a possible application of all-optical magnetization switching as recording mechanism for a high-speed optical memory, in which I will discuss how to increase the efficiency of spin conversion from a photon to an electron and about a possible magical material for an efficient photon to spin conversion. Next, I would like to talk about the importance of efficiency of spin conversion from a photon to electron for recording. In this demultiplexing scheme, only one locally polarized pulse should be recorded. Other data pulses should not influence the recording. Even so, the linearly polarized pulses do not create the spin polarization. They heat up the memory material. When the spin conversion is not efficient, this unwanted heating makes a problem. This graph shows a consequence of absorption of one locally polarized pulse as function of pulse energy. At low pulse energy, nothing happens. At some optimized energy, the pulse reverses the magnetization of the nanomagnet. A pulse of high energy demagnetizes the nanomagnet due to heating, which is bad. In many materials, the efficiency of photon-to-electron spin transfer is poor. As a result, the area of the spin transfer switching is very narrow, and these materials cannot be used in memory because even one linear polarized pulse would demagnetize the nanomagnet and data would be lost. In example, which I have shown you before, even single linear polarized pulse demagnetizes the material. It is not good. The efficiency of spin conversion from photon to electron should be substantially increased. It will be widen this green area and the heating will be no problem at all. So the question is how to increase the efficiency of spin conversion from photon to electron. First, it is important to understand the factors which reduce the efficiency. It might be suggested that the efficiency of spin transfer is always 100%, because the spin of locally polarized photon is just transformed to the spin of the electron. There is no loss of the spin in this process. The efficiency must be 100%, but it's not completely true. Additionally to the spin, a conduction electron may have an orbital moment, and the spin of photon can be transformed either into the electron spin or into the orbital moment, or partly in both of them. There are two distinguished paths for the spin of photon to be absorbed by a solid. For the first path, the spin of photon is transformed into the spin of electrons and does not affect the orbital moment. In this case, the spin of all photoexcited electrons are directed in one direction along the spin of the photon, and therefore the photoexcited electron becomes spin polarized and unable to reverse the magnetization. For the second path, the spin of photon is transferred to orbital moment and does not affect the spin of electrons. As a result, the spin polarization of photoexcited electrons remains exactly the same as spin polarization of conduction electrons in equilibrium, which means that the optical path has no effect on spin polarization of electron gas and therefore on the magnetization. In order for the all-optical magnetization switching to become effective, the optical transition of first type should be enhanced and the transition of second type should be suppressed. It is possible to increase the effectiveness of all-optical magnetization reversal if a material of very specific properties is used. So what are the desired properties of such a magical material for an efficient all-optical magnetization reversal? The first important property is that the optical transition in the material should not be affected by orbital moment. In this case, the spin of photon is transformed into the spin of the conduction electrons, increasing the number of spin-polarized electrons. It means that the difference between orbital moments of the ground electron state and optically excited electron state should be as small as possible. Ideally, the orbital moment should be same for both states. This property is rare in material, but it can be designed or engineered. There are several possibilities for material to have these specific and unique optical transitions. The simplest case is when neither ground state nor excited state have any orbital moment. For example, it is a common case for the localized electrons. The orbital moment of localized electrons in solid is usually quenched, meaning that the orbital moment equals 0. You can check the reason why the orbital moment of localized electron is quenched in this my web page. There is a link to this web page below in description of this video. Since in case of localized electrons, the orbital moment is 0 for both ground and excited states, the spin of photon is fully transformed into the spin of electrons. It is ideal case. However, as I mentioned before, the effectiveness of interaction of photon with localized electrons is very weak because of large difference in the sizes. In metal, nearly all photons are absorbed by conduction and valence electrons. In general, the orbital moment of conduction and valence electrons is not quenched, and there is a large difference between orbital moment for ground and excited states. As a result, a little of photon spin is transformed into the spin of the electron, making the all-optical switching ineffective. There are several methods to quench the orbital moment of the conduction and valence electrons in solid. Quantum wells, quantum dots, and surface states are very effective for that. All these types of electron confinement make a conduction electron similar to a localized electron, and as a result, quenching its orbital moment. Additional possibility is to make a material in which the ground and excited states belong to the same band. That means the ground and excited states for an optical transition have the same orbital moment, and the spin of photon is fully transformed into the spin of an electron. Such an optical transition is called the interband transition and has been used in quantum cascade lasers. This technology is well known and is already commercialized. I should admit that the methods and technologies which allows quenching the orbital moment of conduction electrons are not yet well developed, and I wish more research will be done in this direction. To find or to design or to engineer a material with high conversion efficiency from the spin of photon to the spin of electron is difficult. It is even more difficult to find such a material among only ferromagnetic materials. Ferromagnetic materials is required for storage of data. All examples I showed you before are the cases when both functions, spin conversion and the recording, are realized in one ferromagnetic material. It is not necessary that both functions are realized in a single material. An efficient spin conversion may be done in non-magnetic material, and then the spin-polarized electrons are injected into ferromagnetic material for recording. A possibility to find the magnetic material for spin conversion is higher if the search is extended among non-magnetic materials. For example, I have fabricated and studied the spin-photon memory in which a semiconductor is used as a spin converter. Then the photoexcited spin-polarized electrons are injected in ferromagnetic nanomagnet for recording. The optical transition is simply in a semiconductor, and therefore it is easy to optimize the semiconductor for an efficient spin conversion. You can find more details about this high-speed memory in these YouTube videos. There are links to them in the description below this video. I hope for rapid success for fabrication of an efficient all-optical magnetization switching memory. The high-speed data processing will definitely benefit from such a ultra-high-speed, non-volatile optical memory. Thank you for watching this video.